Training a modern neural network means finding the right value for millions of parameters, and the textbook way to do that is to compute the gradient over your entire dataset before every single step. On a tiny problem, fine. On millions of examples, you would wait forever for one update, and your memory would give out first. So here is the move that made deep learning practical. What if you estimated that gradient from just one random example and stepped immediately? Yet that noisy little shortcut is stochastic gradient descent, and it trains very nearly every network you have ever heard of. Let's break it down. Look, underneath all the theory, this is just a tight little loop, repeated over and over. We pick an example, we take a step, and then we do it again. Follow it one stage at a time. Start at the top. We reach into the training set and grab a single example at random, one image, one row, one sentence. That lone sample is all we are going to look at for this step, which is exactly why each update is so cheap to make. Now compute the gradient of the loss, but only on that one example. It points in the direction that would make the model worse, so we want to head the opposite way. This estimate is rough, since a single point never quite speaks for the whole dataset. Then take a small step downhill against that gradient. New weight equals old weight minus the learning rate times the gradient. The size of that step is the learning rate, and it matters enormously, as we are about to see. Finally, repeat. Grab the next random example, estimate again, step again, cycling through the data many times over. Because each pass makes thousands of these tiny updates instead of one big careful one, the model starts improving almost immediately. So why is this such a big deal? Put the old way and the new way right next to each other. The full batch method computes the exact gradient over all of your training data before it dares to take a single step. Mathematically pristine and completely honest about the true slope. But on a large dataset, it is agonizingly slow, one update per full pass, and it wants the entire thing in memory at once. SGD throws that caution out. It estimates the gradient from one random sample and steps right away, so it makes thousands of updates while the exact method makes one. The path is noisy and zigzags, but it is fast, it scales to enormous data, and it starts improving from the very first example. Strip it all back, and three ideas make this optimizer the foundation of the whole field. It updates from a single example at a time, not the whole set. That choice is what makes it cheap enough to run on datasets with millions or billions of examples, where computing the true gradient even once would be completely hopeless. The steps are noisy, and that turns out to be a gift. Because each estimate is slightly wrong, the path jitters, and that jitter can bounce the optimizer out of shallow local minima and saddle points that would trap a perfectly exact method. It leans entirely on the learning rate to settle down. Too large and the noisy path diverges and blows up, too small and it crawls. In practice, you decay the rate over time, so it explores boldly early and then eases gently into the minimum. Alright, let's lock in what matters. Stochastic gradient descent trains a model by updating its parameters from the gradient of one example, or a small batch at a time, rather than the whole dataset at once. Computing the exact gradient over all the data is accurate but painfully slow and memory-hungry, so SGD trades a little accuracy for enormous speed and scale. The noise in each step is a feature, not just a bug, helping the optimizer escape shallow traps and saddle points that an exact method would get stuck in. Pick a good, usually decaying learning rate, and you have the workhorse that every modern optimizer, from Momentum to Atom, is built on top of. If watching the machinery of deep learning click into place is your idea of fun, we unpack a lot more of it over at standarity.com. Come learn with us.